Okay, so I actually want to talk about a couple of things that we can't spend a whole lot of time, or we're not going to spend a whole lot of time on it during regular lecture, but it's just a couple things that you're we kind of want to know from before. I think most of us probably don't know it from before. It's just different ways to think about stuff you do already know, but maybe haven't done this in this way. When we talk about these two topics, so uh, we're going to talk about them for a few minutes now. There's actually 3 videos related to this. And you know what, maybe we'll go ahead and talk quickly about all 3 of them. The 3 videos that are kind of pre-recorded, if you want to go into more detail, are finding formulas for sequences. So you need, like, given a list of numbers, being able to find a formula for that. And then factorials, which some people have seen and some people have not. And then the last one is absolute value, which is actually going to become the biggest thing that's relevant today. But I want to just talk briefly about all 3 of these. And like I said, there are 3 videos that I've made that you don't have to watch, but if you know that you haven't really looked at this stuff before, it's probably worth going and watching those videos at some point, maybe between now and next week. It's just kind of assumed when you're doing these problems that you're able to, you either have done this before or that you are able to kind of come up with it on your own. I'm not sure how true that is as far as people having done this before, and I'm not sure that it's obvious enough for most of us to come up with on our own. So I would recommend looking at the videos, but just because of the way calc is kind of paced, we can't spend like a ton of time on it during regular class. So I'm going to just give a quick overview of this stuff, and then if you want to go into more detail, you should watch those videos. It's a separate playlist on the YouTube channel. So if you go in and where everything else is, I think I called it Doug's Math Videos, nothing that creative. So under my YouTube thing, then the playlist is called Prereq Material for Sequences. So prerequisite material for sequences. And YouTube doesn't let me arrange the playlist the way I can arrange the videos in the order I want within a playlist, but I can't arrange the playlist. So I think this one's further down in the playlist order because the videos are dated a little bit older. They were made last spring. So anyway, if you want to look at those videos, that's where they are. And in one of the emails, if I send an email today or tomorrow, I'll try to include a direct link to that playlist. So anyway, the quick thing for finding formulas for sequences. So, and you'll see this on the second sequence homework, you'll see some problems like this. So find a formula for the sequence. And so, okay, so number 1 is just going to be the sequence. Let's start with 3, 7, 11, 15, 19, and 23. And like I said, we're going to go through this kind of fast. So if you do have a question, completely fine to ask, but if we need a lot more detail, we should watch those videos. So if we're looking at this, the first thing to do is to kind of determine what the pattern is. And here, to go from 3 to 7, and then from 7 to 11, and from 11 to 15, you're adding 4 every single time. That's an example of what's called an arithmetic sequence, which I do talk a little bit more about in that video. But an arithmetic sequence is one where you add the same thing every time. It's like a linear function. It's not the same as a linear function, but it's like that because it's like a constant slope. And so the easiest way, I think, to think about this is to think, okay, well, an is going to be 3 as the first, or well, we'll call it actually the 0 term. So we'll say this is A0, this is A1, this is A2, this is A3. And so you start with 3, and then you add 4 a specified number of times. So like to get to the second term, to get to A2, you have added 4 twice. To get to A3, you have added 4 3 times. To get to A0, you have not added 4 at all. And so then you can write this as 3 plus 4n, because 4 times n indicates the number of times that you should add 4. And so for A0, you should not add it. For A1, you should add it once. A2, you should add it twice. A3, you should add it 3 times. And so this is an equals 3 plus 4n for n greater than or equal to 0. Or you could write this using sequence notation with the braces, like we were kind of talking about a little bit yesterday, where we go n equals 0 to infinity. Because we're talking about the beginning of the sequence and not just the limit, it does matter where n starts. And so that is one way to do it. There are other ways to do it, but I think that's the most direct way to get a formula for that. Any questions on that example? Okay. And so then the second type I wanted to talk about, so when you add the same thing every time, that's called arithmetic. When you multiply by the same thing every time, that's called geometric. And so if I have, say, 32 and then negative 16 and then positive 8 and negative 4 and positive 2 and so on, the easy pattern there is to think that you're dividing by negative 2. So it's clear that you're dividing by 2, but then it also alternates positive, negative, positive, negative. So you're dividing by negative 2. That's the same thing as multiplying by negative 1/2. So we're doing times negative 1/2 to go from 32 to negative 16, and then times negative 1/2 to go from negative 16 to positive 8, times negative 1/2 times negative 1/2, and so on. And so here you want to think of it as, okay, well, we're starting with 32. And the easiest thing, I think, is to call that A0, A1, A2, and A3, and then A4. And then you need to specify how many times you should multiply by negative 1/2 to get to a given term. So to get from to get to A0, you should not multiply at all. To get to A1, you should multiply by this 1 time. To get to A2, you have multiplied twice. To get to A3, you've multiplied 3 times. And the way you indicate that is you say, okay, times negative 1/2 to the n, because n is the number of times you have then multiplied by negative 1/2. Does that make sense to everybody? Everybody clear? Any questions? Okay, and so we call the one on the top an arithmetic sequence. We call this one a geometric sequence, which will become something we look at a lot. A geometric sequence, again, is one where you multiply by the same number every time. The number that you multiply by is called the common ratio. So the thing you're multiplying by, we call that R. That's the common ratio. And we should kind of be able to see that in general, a geometric sequence can be written in the form an equals a r to the n for n greater than or equal to 0. And that was true back up here too. I should have specified that. Because where a is the first or the 0th term, a is a sub 0, and then you multiply by the common ratio a given number of times. This is not something, I mean, you do want to know that off the top of your head, but I wouldn't just memorize it. So it's something that should make sense. And we want to understand the logic behind that. And we're going to end up using that quite a bit, but not just where you want to memorize a formula. It's where you really want to understand where that's coming from. So again, most calculus books kind of assume you have some background in this. I think most people don't. I think calculus books are wrong about that. So you shouldn't feel bad about it if you do have a question. But if you do need more detail than that, then let's work on it outside of class. And so you can ask a question for sure on these 2 examples, but that's what those videos are in the prereq material. But does everybody understand these 2 examples? Everybody good so far? Okay. All right, and so then the next thing, so these are the 3 topics. Again, I kind of want to just give a quick overview on. The next thing I wanted to give a quick overview on is factorials. And so a factorial is when you write something like this. So if I write 5 with an exclamation point after it, that's red. 5 factorial. And some people, like I said, have seen these, and some people maybe not, but who can give me a quick explanation as to what that means, if you do know?
It would be like, isn't it 1 plus 2 plus 3 plus 4 plus 5?
It's times.
Time,
But
sorry.
No, you're fine, but it's what you said. It's like 1 times 2 times 3 times 4 times 5. For some other reasons, usually you start with the highest number. But when you have a positive integer, you just take, okay, that number and you multiply by all the positive integers less than that. So it's 5 times 4 times 3 times 2 times 1. And if you calculate that, that ends up being 120. And so then, okay, 4 factorial is 4 times 3 times 2 times 1, which is 24. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And I don't remember what that is, but we could calculate that. They do grow very, very quickly. So they're one of the fastest growing functions that we've got. So like when you talk about exponential functions, those things grow very quickly. So like, if you graph 3 to the n, that looks like this, where it grows incredibly fast. Like 3 to the 4th is 81, 3 to the 5th is already 243. 3 to the 6th is a lot, it's 3 times that, so it's a lot bigger than that. Factorials grow even faster because you're doing repeated multiplication, but what you're multiplying by keeps getting bigger. So it's like 1 times 2 times 3 times 4 times 5 times 6 times 7. So when you're talking about n factorial, that goes to infinity and it goes faster than any exponential function. Does that make sense to everybody? It grows faster than any exponential function in the long run. All right, and so one other quick thing on factorials, and you do want to, if you've not seen this type of simplification, you should watch this video because we will use this a lot later. If I have something big, like say 45 factorial divided by 47 factorial, a lot of calculators, most calculators would get overloaded by 47 factorial or 45 factorial because those numbers are so large. And if you go, even if you have one that has like computer algebra system, if you go into the hundreds on the factorials, it's probably going to overload those calculators because they get so big. And so to simplify something like this, with or without a calculator, it's a lot easier to think through what we're talking about. When you have a factorial, because of the way they work, if I have like 38 factorial, I can rewrite that as 38 times 37 times 36 times 35, and I can stop wherever I want and say factorial. Why would it make sense that I could do that? Like, why can I just say, okay, well then times 35 factorial and quit there? Or instead, why would it be okay to do this? Like those are all three the same as each other. Why is that true? Why would that be the same as this and the same as this? What do you guys think?
Numbers following it?
Yeah, because it's like all the numbers following it. So you can think of it as like 38, 37, 36 times 35 down. And then here 38 times 37 down. Does that make sense to everybody? Clear? And so then that means when you have something like this, you can rewrite the bigger factorial in terms of the smaller factorial. And so 47 factorial, I can choose to stop there. Why would it be smart to choose to stop there on this problem?
You can cancel them
Because
out.
then you can
Yeah,
cancel.
now you can cancel them. And so you can cancel the 45 factorials and you can get 1 over 47 times 46. And I'm not willing to figure that out real quick, but you could figure that out real quick, whatever that number is, a lot more easily than dealing with those two numbers independently. And so canceling like that is something that we're going to do a decent amount later. And so if you've not seen this before, it is worth working through the video on this. I don't think it's real long. I think these videos are like 10 or 15 minutes. They're not like full lectures. But it does go through how to do it. Like if you have like 2n minus 1 factorial over 2n plus 1 factorial, how to deal with that. And we'll do that later, and I'll quickly explain it in class, but it will help if you've seen that kind of before. So I would recommend, if you have time, to watch that video. But we need to move on in this class. Does everybody understand this simplification, how I'm getting that? Everybody good? Okay, and so then the third topic I wanted to kind of give a quick overview on is absolute value, and we're actually going to use that today a good bit. Absolute value, there's a lot of topics in math where you look at a problem and it looks really hard, and what you end up doing isn't as hard as what it looks like. It's rare in math that a topic seems easy and is hard, and absolute value is one of those where it seems like absolute value should be pretty straightforward, and it's not as straightforward as it seems. It's not like crazy hard, but it's not as simple as it seems. These are the cases when it is simple. So obviously the absolute value of -4 is what? 4. And the absolute value of 5 is 5. And the absolute value of 0 is 0. There are a couple of ways to think about absolute value. Probably the best way to think about absolute value is to think of it as the distance away from 0 on the number line. So like -4 is 4 units away from 0. 0 is 0 units away from 0. 5 is 5 units away from 0. So that's probably the best way to think about it. Or maybe the easiest way to think about it is you just make the number positive. And so if it's already positive, leave it alone. If it's negative, make it positive. 0 is technically an exception because it's not positive or negative, but the absolute value of 0 is 0. So it's just like you make the thing positive. What's weird is that when you think about this, that obvious answer to that is x. Why is that not necessarily correct? Why
if
is
x was a negative number?
Yeah, because x itself could be a negative number. So like if you just look at that and think of it quickly, absolute value of -x, it seems like it should be x, but it's not, because, or it doesn't have to be, because x may or may not be positive. So like if you look at this where x is -7, and then if you look at it where x is +5, then you get two different simplifications. So when it's -7, the absolute value of -x is the absolute value of -7. That's the absolute value of 7, which is +7. But that's not x. X was -7. And so the absolute value of -x in that case is not x. When you look at it for x equals 5, we've got the absolute value of -x equals the absolute value of -5, which is 5, and in that case is x. Does that make sense? How could I write the one on the left in terms of x without absolute value?
Plus or minus?
Well, okay, in general, plus or minus, but on the left, which one is it? Plus x or minus x? So like this one, is this x or is this -x when you have x is -7?
-x.
Yeah, it's -x. So if x is negative, then the absolute value of -x is -x. If x is positive, the absolute value of -x is +x. So the simplification is weird. It's plus or minus x, but we know when each of those happens. So it's x if x is greater than or equal to 0. It's -x if x is less than 0. And this notation looks weird, but it's just saying, okay, if you know this, then that's the answer. If you know this, then that's the answer. If you don't know which of those is true, then you can't do anything with it. Does that make sense to everybody? Now, what about the absolute value of just x? So I want you to take about 30 seconds, because we can't spend too much time on this, but take about 30 seconds and see if you can come up with this for when it's just x, okay? So what does it simplify to when x is positive? What does it simplify to when x is negative? And then fix it in a minute. Okay, so what it actually ends up being is the same as above. It's going to be x if x is greater than or equal to 0, and it's going to be negative x if x is less than 0. And the reason that is because we can look at the same idea that if x is negative 7, the absolute value of x is the absolute value of negative 7, which is 7. But that's the opposite of what x was to begin with. So we write it as negative x if we want to write it without an absolute value. So when you have negative 7, the absolute value of that is obviously 7, but that's the opposite of x. When you have an x that's positive, so if x is positive 5, then the absolute value of x is the absolute value of 5, which is 5, and so that's x. And so that's something that's weird to think about because it seems like absolute value, like especially when you're doing it here, it's real easy. When you're doing it with variables, it's not as obvious what happens. And when you have x in general, like if you're taking an algebra class and you're saying, okay, or you're working with algebra and you're saying, okay, the absolute value of 2x minus 1 or 4, say, equals 7, that's a weird equation to solve. And the reason it's a weird equation to solve is because we don't know whether x is positive or negative. Does that make sense to everybody? So I don't want to take time to review that equation right now, but what I do want to talk about is if I'm looking at this. So when we're doing sequence limits, if I look at, say, the absolute value of, say, 5n squared minus 6n, then most of the time, like when I'm looking at absolute value of 2x minus 4, we don't know whether that's positive or negative. So to simplify that, we don't know how to do that. But for sequences, we do. And it's because we're dealing with the limit as what happens. What do you guys think? So when we're talking about sequence limits, like we were doing yesterday, we're talking about the limit as n does what?
Approaches infinity.
As n approaches infinity. So we know whether this is positive or negative. 5n squared minus 6n, as n goes to infinity, is that going to be positive or negative? What do you guys think?
Positive.
It's going to be positive because 5n squared is going to be bigger than 6n when n goes to infinity. So then the absolute value of this is itself when n goes to infinity because that's positive. Does that make sense to everybody? Okay, now I want to amend that in a second. But now what if I have, say, 40 minus n? As n goes to infinity, is the inside of that going to be positive or negative?
It's going to get more and more negative.
It's going to get more and more negative. So because that's negative, the absolute value of that is negative parentheses 40 minus n, which simplifies to n minus 40. Does that make sense to everybody? Now, what's the problem with what I just wrote? So, like, is this always true? Is this always negative?
No.
No.
It's not. This is true when n is what? As n approaches
Greater
infinity.
than 40.
Yeah, n's got to be bigger than 40 for this to work. It actually could be 40. So if it was 0, it can be either of the simplifications. But
Greater than or equal to.
Yeah. So this is true if n is greater than or equal to 40. Does that make sense to everybody? This one on the top is true for most n that we're dealing with, but what n would it not be true for? This is true if n is greater than 1 or greater than or equal to 2. So if n is 1, that's negative, so it doesn't work. But if n is bigger than 1, then 5n squared is bigger than 6n. And so then that does work. And so what we don't want to do, what we're dealing with on sequences is we're dealing with the limit as n goes to infinity. So we actually don't care. And so like what Max and I were just saying, okay, it's 40 or 41. We don't really care about that. What we do care is that in the long run, it's true. And so rather than spending time trying to figure out when that's true, what we typically do instead of this is we just say for large n. And that just means we know it's true eventually, but we don't want to mess with trying to figure out when it starts being true. Just once n's big enough, then okay, it's true. So when we say for large n, how large? Large enough for us to be right. Does that make sense to everybody? I know that's weird because it's not as exact as we usually are in math. But as we're talking about n going to infinity, we can say things like that because we're saying, okay, well, we know n's going to get big enough eventually for this to be bigger. And it's important for problems like this. So if I have this where I have, say, n to the third minus 456n squared minus 241,345n. Let's do, yeah, that's fair. Let's do that. So we talked a lot yesterday about like the biggest thing. For large n, what is the biggest thing in that absolute value? When n gets really, really big, what's the biggest thing? What do you guys think?
N cubed.
N cubed. Now, that means that in the long run, is this going to be positive or negative? When n gets really, really big, if n to the third is the biggest, is that going to be positive? Because these are pretty big over here, right? So is that going to end up positive when n goes to infinity? Or do we not know?
It would end up positive.
It would end up positive because n to the third, remember n's going to infinity. So we're talking about n being like hundreds and hundreds of billions and hundreds of billions factorial. So like way bigger than this. Does that make sense? So in the long run, this is positive and it's huge. So that means this is equal to n to the third minus 456n squared minus 241,345n for large n. How large? Pretty big, probably, right? Because like even 10 to the third is like 1,000. Well, that's not bigger than 10 times this. Does everybody see that? Or 10 squared times this. So like even when n is 10, this is still negative. When n is 100, I don't know. We'd have to figure it out and see. But eventually, n to the third's bigger than those. So we just say large n because we know eventually that one's bigger. So then, okay, we know it's eventually positive. But we don't want to mess with knowing whether it's 40 or 100 or 97 or 2,000 before it's true. Does that make sense to everybody? We may be able to figure it out, but we don't need to. Does that everybody understand? All right. Any questions? Okay. So we're going to see that a good bit. I want to go back to doing some problems. And absolute value, we've now talked about it a good bit, but there's some more examples of that in that video on the YouTube channel. So, all right. So what I want to look at next is problems again, where the directions are show whether the sequence converges or diverges. and if it converges, find its limit. Man, that says it diverges. It's supposed to. All right. Okay, so number one is going to be this one. All right, so yesterday we talked about ones where you had fractions and all of the function types were the same. So you had like all power functions or all exponential functions. This problem is artificially different from that. It ends up being basically the same thing, but you have cosine, which freaks everybody out because it's trig, but it's the same stuff. We're talking about cosine of this. And so what we do here is we say, okay, cosine of 6n minus 7 over 5n squared plus 1, we look at what happens inside. So the inside, we pick the biggest thing on top, biggest thing on bottom. So the biggest thing on top is what as n goes to infinity?
6n.
6n. And the biggest thing on bottom is what as n goes to infinity?
5n squared.
Perfect. And so then we simplify that and get cosine of 6 over 5n. Okay, as n approaches infinity, what happens to 6 over 5n?
To 0.
Yeah, it goes to 0 because it's 6 over infinity. So we can say, okay, well, then this approaches cosine of 0. But cosine of 0 is what?
1.
1. And so then the limit of this is 1, and we just gave a quick proof or a quick explanation as to why the sequence converges and that it converges to 1. And so, okay, that's it. If we have this problem, okay, then let's think about what happens. This time, it's not artificially different from yesterday. Here, it's just cosine of something that we know how to do. And so we knew how to do the thing inside, and we knew the limit of that was 0. So then, okay, it's just cosine of 0, which is 1. This one's different because as n goes to infinity, n over 4 also goes to infinity. Does everybody see that? So what happens to cosine as cosine of whatever as you take cosine of something that's going to infinity? So cosine of infinity, what happens as you go to the right on a cosine graph?
It just undulates.
Yeah, it just oscillates like between 1 and -1. Does that make sense to everybody? So it just bounces at these random values, relatively random values between 1 and -1. And so then that's not going to go to anything. That's not going to converge unless it's a very specific set of dots. Like maybe if it was all the dots at the top of the cosine graph. But like cosine does that. And so, whoops, not like that. But anyway, it goes forever to the right and just keeps bouncing around. So that's not going to approach anything. It's just going to go between two values. Okay, so then this isn't as obvious like it was yesterday. But if that happens up here, what's the bottom doing? So the top is always between 1 and -1. What does the bottom do as n goes to infinity?
Goes to infinity.
It goes to infinity. So like when n is something huge, so like if n is 500 billion, okay, the top is cosine of 500 billion over 4 radians. That's some random value between 1 and -1. So if n is 500 billion, you've got something between 1 and -1 over 500 billion squared plus 8. What's that? Give a number between 1 and -1 over 500 billion squared. We guys think?
0.
It goes to 0 because the top's always between 1 and -1. The bottom is n squared plus 8, which goes to infinity. So then it's going to 0. Does that logically make sense to everybody? We clear? Okay, now you can't say it as cleanly as what you do up here. It's not like we could say, okay, well, the top just goes to 6 over infinity, but it's the same thought process. Instead of going to 6, it's between 1 and -1. It just doesn't go to anything. So what we do is we write this. We say, okay, this is between -1 over the bottom and +1 over the bottom. Is everybody clear why that's true? Good? Okay, and now we know this one goes to 0 and this one goes to 0. So we're going to say, okay, well, -1 over n squared plus 8 goes to 0, and 1 over n squared plus 8 goes to 0. Well, if it's always bigger than this one and always smaller than this one, then it's always between those, so then the original one goes to 0. So cosine n over 4 over n squared plus 8 goes to 0. Does that make sense to everybody? What's this called?
Isn't that the intermediate value theorem?
Not that, but close. Sorry, that's a different way you learned in Calc 1. This is similar to something like that. Yeah, squeeze theorem. Somebody say it in the chat. Are you guys not able to chat publicly? My bad. I changed that last night and forgot to change it back. All right. So anyway, yeah, it's the squeeze theorem. So we say by the squeeze theorem. Graphically, the idea of the squeeze theorem is, okay, we have this bottom one that's smaller than everything and increases towards 0. So let's put an axis in here. And then you have this top one, 1 over n squared plus 8, that decreases towards 0, so it goes to 0. And then the middle one, the one in blue, is cosine, and so it's bouncing, but it's over n to the 4th plus 8. So it's between those the whole time. So then it gets crushed or squeezed in towards 0. And so that's why it's called the squeeze theorem, and that limit has to be 0. But you say, okay, well, my logic is explained in the squeeze theorem. So that's it. Let's state the squeeze theorem. All right, so the squeeze theorem says that if all right, so the way we're going to state it is, okay, the question in chat is, do we have to write all of that every time? So yes, if you're asked to provide a proof or an explanation, then you should write all of that every time, and we'll see how that corresponds to the squeeze theorem. If you're just trying to find the limit and not ask for an explanation, you don't need to write all of that. You need to give some quick explanation, but not like a formal proof. Does that answer the question, Nick? Just depends on what you're asked to do.
Yeah.
Okay. All right. So when we set up these theorems, we're going to try to have AN be the original sequence in practice. It doesn't, I guess it doesn't have to be, but normally AN we're going to think of as the original sequence. So we've got BN and CN, one smaller and one bigger. Okay, so if that's true, and we'll say, yeah, that's fine. We'll use several ands. Limit as n approaches infinity. Make that actually look like m or n of Bn is equal to the limit as n approaches infinity of Cn is equal to L. Okay, so let's say exactly what this is saying. So it's saying AN is between Bn and Cn. So like here, AN's this, Bn is this, Cn is this. And then Bn and Cn both go to some number L, like in this case, 0. Then what has to be true? Then AN goes to L as well. Does that make sense? Does not generally have to be 0. A lot of times on problems we actually do, it's 0, but it doesn't have to be. It could be any number you're getting a squeeze between. But these outside ones, Bn and Cn, those do both have to go to the same number. So they don't have to be 0, but if this one goes to 4 and this one goes to 8, that doesn't help because it could bounce between 4 and 8, but it does have to go to the number L, whatever that is. All right. Any questions on the squeeze theorem? Okay. And so another answer to the question, do we have to show all this every time? If you're doing a proof or showing it, you need to show that everything in the if statement is true. So you need to show this or explain this. You don't maybe need to explain why, as long as it's true, but you need to show that that's true. You need to find these two limits, and they need to be the same thing. Remember yesterday we talked about the arrow is the same notation or means the same thing as this. And then that means that this is true. So because of those three things, then okay, we can conclude this. I'm using arrows here rather than the limit notation, but that's okay. We said that was interchangeable yesterday. All right. Any other questions so far? How do we know to use the squeeze theorem? Micah, the question is, how do you know when to use the squeeze theorem? That's a good question. You can't give a definite rule. A lot of times it's when you have sine and cosine, because those are between 1 and -1. It doesn't guarantee that you're going to use the squeeze theorem, but like back up here, obviously this one we did not. But here, if you think through the logic that the top is bounded between 1 and -1 because cosine's always between 1 and -1, and the bottom is going to infinity, like that thought process we used before we even said the word squeeze theorem, that process is the idea behind squeeze theorem. That's a really good time to know when to use it. Does that help some? Like there's not a definite answer.
Yeah.
Okay.
Repeat that.
Okay. Other questions?
Could you repeat what you just said about that mindset thing?
Yeah, sure. So like the question is, how do you know when to use squeeze theorem? And there, it's like integrals. There's not a definite way to know. You always have to use U sub or you always use trig sub. Same deal here. There's not a way to say, okay, well, you always use squeeze theorem in this case. But like when we were first talking about this problem, I didn't write the word squeeze theorem. I didn't mention the word squeeze theorem until after we had done all this. So like when you think about this problem as n goes to infinity, the thought process is that, okay, cosine of n over 4 is between 1 and -1. The bottom goes to infinity. So if the top is between these two values and the bottom's going to infinity, that means the thing has to go to 0 because this is caught between two things that are going to 0. That exact thought process is the idea of the squeeze theorem, and that's when you use it. It's just there's not a definite, know all time to use it. Does that make sense? Does that help some?
Yeah.
All right. All right. So I want to talk for a second about a general sequence AN versus its absolute value, okay? Now, AN is a bunch of numbers. So it could be a sequence like 1, 2, 3, 4, 5, 6, 7. Or it could be a sequence 1, 1/2, 1/3, 1/4, 1/5. Or it could be -1, -2, -3. Or it could be -1, -1/2, -1/3. Or it could be +1 and then -1/2 and then +1/3 and then -1/4. So we don't know, but the sequence AN could be a list of a bunch of values. Okay. What would happen if we have a sequence like, so let me write a couple examples of what AN could look like. So if we have AN, if it's like 1, 2, 3, 4, 5, that's an example of a sequence. 1, 1/2, 1/3, 1/4 is another one. 1, 1/2, we'll do -1, -1/2, -1/4, -1/8, and so on. We have 1, -1, 1, -1, 1, -1, and so on. And then we could have one where it's like 1, -1/2, and then 1/3, -1/4, and then 1/5, -1/6, and so on. And so when you look at AN, that represents all of the numbers, like A1, A2, A3, A4, and so on. It's the whole sequence. When you look at the absolute value of AN, what do you think that does? What is that? It's a different sequence, but what is it? What does it do to all the numbers? What's absolute value do to a number in general?
Makes it positive.
It makes it positive. So like if I look at AN versus absolute value of AN on this first sequence, the absolute value of that sequence is itself, because all the terms are positive anyway. So when you take the absolute value of them, none of them change. Does that make sense to everybody? Okay, what about here? If I take the absolute value of all those, does anything change? No, same sequence. What about here? What happens when I take the absolute value of those? Same sequence or different? It's different. It's 1, 1/2, 1/4, 1/8. Does that make sense? Okay, what about this one? If I take the absolute value of all those, what does the sequence become? Go ahead.
Just 1, 1, 1, 1, 1.
Yeah, the absolute value of that sequence
There is no sequence.
Well, there is, but it's a very simple one, 1, 1, 1, 1, 1. And so then, okay, this one, if I take the absolute value of it, it becomes this one. Does that make sense? Okay, so then do we see why this would be true? Why would that be true? So that means all the terms in AN are less than or equal to the corresponding term in the absolute value. Does that make sense to everybody? Why would that be true? Could it be equal? Sure. So like on these, if you take the absolute value, all of them stay the same. On these, they're all less. The original one is less than the absolute value because they all become positive. Here, some of them are the same, some of them are smaller. But this statement's true. Does that make sense to everybody? Yes, good? Okay, how does it compare to this? So if I have the absolute value of AN, but then I put -1 in front of it, then what could I write to compare those two sequences? Yeah, they're all negative. So Andy say in the chat, if you put that negative absolute value, it makes every term negative. So this becomes -1, -2, -3, -4, -5. This one stays the same. This one becomes -1, -1, -1, -1. So then, okay, what's the relationship? Which one's bigger, or do we not know? Which one's bigger than or equal, or do we not know?
The regular AN's bigger than or equal to.
Yeah, so the AN is bigger than or equal to negative absolute value of AN. Does that make sense? So this inequality is true for all sequences. Does that make sense to everybody? That's true for all of these. The original sequence is less than or equal to its absolute value, and it's bigger than or equal to the negative of its absolute value. Now, we don't know which, but we know one of those things is true. Does that, everybody follow that? Okay, so then why am I talking about this right next to the squeeze theorem and right after we talked about absolute value earlier? So absolute value we were talking about earlier because we were going to get into this. But what does this have to do with the squeeze theorem? For every AN, you've now got two things that would work for the squeeze theorem. Does that make sense? Everybody clear? Okay. Now, for the squeeze theorem to work, the two limits of the ones on the outside, the BN and the CN, those limits must be the same as each other. Does that make sense? Okay, they have to be L, meaning they have to be the same as each other. Now, not every squeeze theorem example is going to be using this, but what I'm saying is that this always satisfies part of the squeeze theorem. Could this ever happen? When would, is this possible? Can that happen? So remember, this makes them all positive. This makes them all negative. So is there any way for those limits to be the same?
0.
If it's 0. Does that make sense to everybody? Okay, so if it's 0, then they're the same. If it's not 0, there's no chance they're the same. If this one goes to 5, this one goes to -5. Does everybody see that? Okay, so for this to be satisfied, though, if this goes to 0, automatically this one goes to 0. So, okay, so what if I tell you that I know for some sequence the absolute value of an goes to 0. So we have some random other sequence that I'm making up. I don't have it on the screen anywhere. But for that sequence, its absolute value goes to 0. Then, okay, we know this is 0. What would this have to be? If this goes to 0, what does -1 times it also go to?
0.
0. So, okay, if this goes to 0, this is automatically true. Does that make sense? Okay, this is also automatically true. No matter what, this is true. Whoops. This inequality is true regardless of whether the absolute value goes to 0 or not. And so what that means is if this is true, all of this is true, so then an goes to 0 by the squeeze theorem. Okay, that idea is called a corollary to the squeeze theorem. Corollary in math, theorem is like a big result in math. Corollary is a smaller result that might be important, but follows directly from a bigger theorem. So because of the squeeze theorem, we can make a simpler statement about something else that says that if we can prove that the absolute value of a sequence goes to 0, then this sequence itself, whoops, not the absolute value, this sequence itself goes to 0. Okay, so this is another thing that's true. It follows directly from the squeeze theorem, but it means we can do a problem like this. All right, so we're going to go back to problem 3. Directions again on this problem are show whether the sequence converges or diverges. If it converges, find its limit. So number 3 is going to be an equals -1 to the n times n over 4n minus 7. Okay. And something we should have figured out on the homework a couple nights ago is that -1 to the n, if I have that sequence, that is the sequence 1, -1, 1, -1, 1, -1, depending on where you start. But -1 to the 0 is 1, -1 to the first is -1, -1 squared is 1, -1 to the third is -1, and so on. It alternates 1 to -1. When you take that and you multiply by something that's eventually positive, then the sequence alternates positive, negative in the long run. Does that make sense? Okay, that type of sequence is an example of what's called an alternating sequence. And you know what? No, never mind. It's an example of what's called an alternating sequence. When that happens, the techniques that we've used so far don't work directly, although you could use the squeeze theorem. But what's quicker is to immediately take the absolute value of the sequence. So we're going to do this. We're going to say, okay, I want to look at the absolute value of an. If you have an alternating sequence, this is almost always what you want to do. I want to look at the absolute value of an, but in no way is this equal to this. So you need to indicate in your explanation that you're not saying, okay, this is the same as this. You're not. That's not the same. But you're going to say, okay, I don't like dealing with this, so I'm going to deal with this instead. So what I usually say is consider the absolute value of an, meaning, okay, we're going to think about this instead. And now we're going to figure out what that sequence is. Well, if an is, if you have -1 to the n and it's this, what's the absolute value of all those?
1.
1. So the absolute value of this part is 1. What's the absolute value of n? So n is, as n goes to infinity, is n positive or negative? Positive. And so the absolute value of n is n. 4n minus 7, can we tell whether that's positive or negative as n goes to infinity? That as n goes to infinity, which is bigger, 4n or 7?
4n.
4n's bigger. In fact, as soon as n is 2, 4n's bigger. So for large n, the bottom is positive, which means its absolute value is just itself. Again, kind of what we were saying earlier, though, is that absolute value looks easy and can be more complicated than it looks. What it looks like you're doing is just dropping this, and that's not always what happens. So you have to think through whether everything is positive or negative, and this is positive for large n, and I won't always write this. But we're thinking, okay, for large n, we know that's positive. Oh, my fault. You know what? Please do not change problems when you're taking tests or doing homework for me. But we're going to pretend like that was n squared to begin with. And then we'll talk about what if it weren't n squared, okay? All right, and so now what I want to do is I want to say, okay, what is the limit of this? And so we can do this like yesterday because it's now one where it's all the same type. It's all power functions. So this approach is n over 4n squared, which goes to 1 over 4n, which goes to 0. Does that make sense? Everybody good so far? Okay. So then, what's the answer to the original problem? And somebody explain what it is and why.
It has to be 0 since the absolute value of an goes to 0.
Exactly. So an goes to 0 because the absolute value goes to 0. So this corollary says, okay, if the absolute value of an goes to 0, then an goes to 0. So if you take the absolute value, you figure out that it goes to 0, automatically this goes to 0. That's because of the squeeze theorem. But based on what we were saying up here, all the squeeze theorem stuff's automatically true if the absolute value goes to 0. So then the original goes to 0. Does that make sense to everybody? Okay, now let's go with the problem that I originally had written. And we'll do it on the right-hand side of the screen. All right, so I originally wrote that. And so we're going to do this same way at first. So we're going to say consider the absolute value of an. That's n over 4n minus 7 for large n, like what we said. That now approaches n over 4n, which approaches 1/4.
Yeah, I was going to say.
I want you to look at what I wrote and think about why that's wrong. Okay? I want you to think about why that's wrong based on what we have said. Maybe we haven't said, well, okay, why can we not make that conclusion based on what we've said? We maybe not.
Your corollary is conditional specific to 0.
Yeah, so the absolute value has to go to 0 for this to work. Does that make sense to everybody? So read carefully what this says. So it says that if the absolute value goes to 0, then the sequence goes to 0. What does it tell you about when the absolute value does not go to 0? Nothing. It says nothing about it if the absolute value doesn't go to 0. Does that make sense to everybody? Okay, so then let's think about what's going on. So if this is true, which it is, the absolute value goes to 1/4. So then when like n is 100 billion, the part without the -1 to the n, this part, when n is 100 billion, or when n is bigger than that, when n is 100 billion to the 100 billionth power, then this part is basically 1/4. Does that make sense? But then it's multiplied by -1 to the 100 billion. So if n is 100 billion, this part's 1/4, and then this part is -1 to the 100 billion. What is -1 to the 100 billion?
1.
+1. So then this whole thing for 100 billion is basically 1/4, because it's 1 times a fourth. Now, what about if it's 100 billion and 1? Then, okay, when n is 100 billion and 1, this is basically 1/4. But what's this?
-1/4.
-1 times that, so -1/4. So if
Yeah.
it's, you're right, though, we said right. So it's
I skipped a
-1 to
step.
the, you're fine. -1 to the 100 billion and 1 is -1, and then times 1/4 is -1/4. So somebody give me a quick explanation as to why that helps us figure out the answer here. What happens? So remember, when it's 100 billion, it's +1/4. When it's 100 billion and 1, it's -1/4. What do you think it is when it's 100 billion and 2?
Does that mean it diverges?
It does.
Because it never finds one point.
Exactly. So it diverges because it alternates 1/4 to -1/4 for large n. Or we'll say as n goes to infinity. And not exactly 1/4. And not exactly -1/4, but like, okay, positive 0.24999999998, and then -0.24999999997, and so on. And so it's alternating, bouncing positive 1/4 to -1/4, which means it never closes in on one number, so it diverges. Does that make sense? Questions so far? Okay. I'm going to put one on the screen and like you guys try it. Okay. I'm going to give you about a minute. See if you can do it, and then fix it in a minute if you're wrong. Okay, so if you're good, keep working. I'm going to start working the problem out. So we're going to say, okay, consider the absolute value of an. That's this. So an diverges because it alternates 5/8 to -5/8. Check closely what you're doing versus what I've got on the screen. And please let me know if there are questions. Something weird happened.
You factored out a -1.
So it's okay. I'm not factoring a -1 out. What I'm doing is I'm trying to figure out the absolute value. So the absolute value of -1 to the n is +1. 5n squared is positive. So the absolute value of that is itself. But 7n minus 8n squared is negative. So the absolute value of that is -1 times the whole thing. Does that make sense?
Yeah.
Okay. And so then I distributed the negative and got to here, so we got 5/8. If you worked this out and got the absolute value goes to -5/8, that doesn't seem weird, but if you think about it, absolute value cannot possibly go to -5/8 because absolute value is always positive or 0. Does that make sense?
Yeah.
Can we go through like the whole problem and then change it to positive at the end? Or is it necessary to do it in the middle?
I mean, you probably can figure out that's going to end up with the right answer almost every single time, but you should do it this way because if you're saying the absolute value is if you wrote this, so I would expect a lot of us wrote this, and I understand why. But if you write that, that is technically not true. That's like saying the absolute value of 7 is -7. Do you see what I'm saying?
Yeah.
Okay. And so like, if you do what you're saying, like you're going to get the right answer. So if I do a problem and say, okay, I'm doing the absolute value or absolute value of, 7, and I put -7, and then I say, oh no, I know it's going to be positive, and change it to 7 at the end. That just means your work technically is wrong and you knew that it had to be positive. Does that make sense?
Yeah, no, that makes sense.
Okay, so we should not, technically this is not right, and we should do it this way, okay? I know it's a weird technicality, but that's the stuff we were talking about in the absolute value at the beginning of the video, and there is that separate video on it that is probably worth going through, all right? Any other questions on this? Now, what if this had been 5n squared over 8n to the third? So what if this had been n to the third here? What would have happened? Instead of 5/8, what would you get here? You'd get 0, which would mean this would go to 0. So remember, what the corollary actually works for is if the absolute value does go to 0. If it doesn't, and it's alternating, then it's going to diverge, and so we can figure that out. Okay, so I want to talk about what we should be doing next before tomorrow. So please, before tomorrow's lecture, finish the sequences 1 worksheet. And that is more important right now than the WebAssign. I know you have to do the WebAssign, and I know that's annoying, but if you haven't done it or haven't started that, I would still wait on it. I would get this worksheet done first. If you look at it real quick, there are several. So I think we got you through 16 yesterday. We did 17 through 20 are like the very first example we did today of the sequences where like really it's not any different from before. But I do want you to compare what's there versus, I want you to compare versus my answers. Make sure you understand how I'm getting the answers. 21 and 22 are similar to Squeeze Theorem, or they are Squeeze Theorem. And then 23 through 27 are alternating. And then I want you to think about 28 through 32. Some of them are alternating. Sometimes there's weird stuff happening. But we're done talking about the stuff on this sheet. We're also done talking about the stuff on the first WebAssign, but we're farther than what the first WebAssign covers. So the second WebAssign, I'm going to purposely wait and post that tomorrow. That one will be due Monday, but it'll cover the stuff from today, from tomorrow, and then on monotonic and bounded, which is Friday's topic. So we are not going to hold a live class Friday, but I'm going to send a video for Friday. Because of the test last week where we cut Wednesday, we have to cover monotonic and bounded this week. We're not going to do it live. We're going to just do a video. It's not the most important topic ever, but it's something you're going to need to watch the video on. So I'm sorry to be kind of piling on work this week. We've got to get through sequences this week so we can start into series next week. If you have questions, stick around. If not, that is it for today, and I will hopefully see you guys tomorrow. Thanks, you guys.